morning, all of you. So we are discussing about classifications of turbine. So next one is your fourth one, that is the head of water available. According to it, how turbines are classified. First one is your low head turbine that ranges from the head is between 3 meter to 50 meter. So first one is your according to head of the water available. First one is your low head turbine. That is the head available is at the inlet, that is 3 meter from 3 meter. From 3 meter to 50 meter. And generally propeller turbine and Kaplan turbines falls in this category. Next one is your medium head turbine. Medium head turbine, the head between available at the inlet is between 30 meter to 500 meter. And Francis turbine is the example of this medium head turbine. Next come to next category, that is your high head turbine. Next is your high head turbine. These turbines operates above 100 meter of head. So the head available at the inlet of the turbine, that is above 100 meter. And Pelton wheel is your example of this high head turbine. Next one to these are the turbines typically you can see here. Pelton wheel, Francis turbine and Kaplan turbine. These are the common type of turbine. See first one, that is your Pelton wheel turbine. This is your impulse turbine. So what is the energy available? That is kinetic energy. And head available, that is high head, that is between 50 meter to 1000 meter. And discharge is low. Direction of flow, that is tangential to the runner, and specific speed is low. Next one is your Francis turbine and Kaplan turbine. Both are reaction turbine. I have told you already in the starting, turbine can be classified as impulse turbine or reaction turbine. So Francis turbine is your next turbine, that is your reaction turbine. So what is the energy available of the Francis turbine? Kinetic plus pressure energy. So Francis turbine is your medium head turbine, that is water available at the inlet is 60 meter to 150 meter. And discharge is medium. So direction of flow, it may be radial flow or mixed flow, and specific speed is medium, that is 60 rpm to 300 rpm. Next is your Kaplan turbine, that is also your reaction turbine, and type of energy available, that is kinetic energy and pressure energy, and head is low, that is below 30 meter. Discharge is high. Direction of according to direction of flow, this is your axial flow turbine, and specific speed is high, that is 300 to 1000 rpm. Next come to your different type of turbines and their constructions. So first one is your impulse turbine. See it? The impulse turbine pattern will comes under the impulse turbine category. So next come to your first pattern wheel turbine. We will discuss about the construction of pattern wheel turbine. So you should know what is pattern wheel turbine, what is the specification. This is the high head and low discharge type of water turbine, and it was developed by L.A. Pelton in 1989. So what the name is the Pelton wheel turbine. So these are the main components of the Pelton wheel turbine. First one is your first main component, that is the runner with the buckets or hands, which is fixed at the periphery of the runner. Second one is your the nozzle assembly with control sphere and deflector. We will see in details. Next one is your brake nozzle or braking jet. Fourth one is your AC. Next come to your first one, that is your, now see the diagram of pentagon. This is your line diagram. The outer periphery, this is your casing. This one is your brake nozzle, and this is your shaft, horizontal shaft. To the shaft, this is your runner, and to the runner, these buckets are attached. These buckets or vanes, these are called the, these are attached to the runner. This is your assembly of the nozzle. This is spear, this is deflector, and this is your tail race. Tail race means the water comes from the turbine and to which it flow through, that is your tail race. Next come to your the same figure. Let's come to next part. So static, your first part is your runner with buckets. So what is a runner? Runner is a circular disc that is mounted on a shaft, and on which periphery the buckets are fixed and equally spaced. The buckets of the vanes are fixed on the periphery of the your runner, and runner is mounted on the shaft. So maybe buckets are made of iron, cast steel, bronze, stainless steel, depending on the head of the inlet of the turbine available. What is the head available? That is the deciding factor of which material the buckets will be made. The water strikes at the bucket on the splitter of the bucket or gets deflected to angle alpha 160 degree or 170 degree. So let's see the picture. See, this one is your shaft. Okay, this shaft is your horizontal. To the shaft, this is the runner. This runner is fixed to the shaft, and to the runner, these buckets are fixed. These are the buckets. So this is the actual picture. This is the line diagram. This one is your runner. This is your shaft, and these are the buckets. So how to calculate the number of buckets on a wheel? The number of buckets that is defined as Z. Z is equal to D divided by 2B plus 50. What is your capital D? Capital D is your runner diameter and small d is your Z diameter. These are the dimensions which are given but not necessary for you. Let's continue to the next part, that is your nozzle assembly with controls, spear and deflector. That means that is the total assembly through which the water jet is striking into the pockets of the wheel. So what is happening here? Water brought from the hydroelectric plant to the dam to the penstock, through penstock at the end of the penstock, where at the end of the penstock the nozzle is attached, which converts pressure energy completely into kinetic energy. What is happening in your nozzle? The pressure energy available at the inlet of the nozzle that is completely converted into kinetic energy. Okay? So in your nozzle, what is happening? Pressure energy is converted to kinetic energy. So this converted high speed jet which strikes to the vanes, and vanes are mounted to the periphery of the runner. So the high speed causes kinetic energy jet striking into the pockets of the runner. Next, what amount of water will be striking at the pockets of the runner, that is controlled by the adjustment of the spear. Water flow rate is controlled by the forward or backward sphere. We will see in detail next slide. What is sphere? See here. This is your penstock. Penstock is your carrying water from the tank to the turbine. At the end of the penstock, the nozzle is fitted. This is your nozzle, this is your penstock, and this is your sphere mechanism. See, this is your increasing area and decreasing area. If I turn this wheel, then sphere may come backward or forward. According to this motion, the water flow to the runner, the pocket of the runner is controlled. Next come to brake nozzle or braking jet. So if we want to stop the turbine, so what will you do? Simply stop the water flowing to the turbine. So even after you are stopping the water or controlling totally the water flowing into the turbine, it may not stop due to the inertia of the turbine. So that's why the brake nozzle or braking jets are provided. So to stop the turbine in short time, the brake nozzles are provided, and that is why it is called as braking jet or brake nozzle. Next part is your casing. Casing means the outer part. You have already seen in the picture. That is the outer part of the turbine. So it is mainly made of your cast iron or fabricated steel plates. The main function of your casing is it is providing cover. Cover means your dust particle and foreign particles may not go into the turbine. And again, in the meantime, it is preventing the splashing of water. That means whatever the water is striking in the veins of buckets of the runner. So it is preventing the splashing of water. And last one is your to discharge the water into tailways or downward. That means your casing is guiding the water, whatever water through the turbine passing, that is guided by your casing towards the down or towards the tailways. Next comes the power development in the Titan wheel turbine. So first one, the bucket splits the jet into equal parts and changes the direction of the jet by 165 degrees. There is a particular water striking. Suppose this is your bucket, water is striking like this, and water is splitting in two halves. Suppose this is your pocket. So water coming through this direction and splitting in this direction and in this direction. This is the shape of your pocket. Water is coming axially through this, and water is splitting in two halves, in this direction and in this direction. That is your 165 degree angle. This is already made permanently. I will show you the velocity diagram of a phantom turbine blade. The diagram shows the conditions that is your heat or I will discuss it. In this case, the jet direction is parallel to the blade and velocity or the tangential velocity of the runner. This is your velocity diagram. One, that is representing your, this is the one half of the bucket. This is the lower half. So water or jet entering to this and is going out for this. So V1, VU1, these are your 1, that means that is your inlet, and 2, that is representing your outlet. So U is your initial speed, and V1 is your velocity of the rocket, VU1 is your VR1 is your relative velocity, likely. This is your water is going axially, that means this angle is 0, and this is deflecting at 165 degree, what I have told you already. So this is your velocity triangle of the petrol wheel turbine. This is your initial velocity U of the rocket, and this is your beta angle. This is your deflection angle. Water is getting deflected by beta. Okay. Here you can see from the velocity diagram, VU1 and V1 these are same. So V relative velocity at the inlet, that is equal to V1 minus U. Next, in the ideal case, the VR2 is equal to VR1. That means relative velocity at the inlet is equal to relative velocity at the outlet. And U2 is equal to U1. That means the initial velocity of the rocket run off at inlet, that is equal to initial velocity of the rocket at the outlet. But if there is friction, obviously there is friction, then the relative velocity at outlet, that is K into V into R. K is there some constant, and K is given as the friction constant. H is equal to rho Q V1 plus VU2. Next come to your T, torque generated. What is your torque? Torque is generated force into distance. F is your force. This is your force. Force is rho Q into velocity. VU1 plus VU2. So what is your torque? Torque is F into R. R is your radius. Force into distance. Force into radius. This is your force into radius. P, power developed, is equal to force into your velocity. That is, this much is your force into your velocity. Now come to efficiency of your jet. The efficiency of jet is defined by output per second divided by input per second. When in maximum, whatever actual efficiency is given as output by input. So efficiency of your jet is given by work done per second divided by input per second. So work done per second is equal to the power output jet, which is, we have already derived rho Q VU1 plus VU2 all multiplied into U. So input to the jet per second, that is equal to, what is the input? Input is your kinetic energy, isn't it? The pressure is converted into kinetic energy at the nozzle. So what is the kinetic energy available? Half rho A V1 into U1 square. That is your half rho A V square. So your hydraulic efficiency is given as, this is your work done divided by the input jet velocity. Finally you get this one. That is your 2U multiplied VU1 plus or minus VU2 divided by V1 square. In your next class, I will discuss about the other parts of these calculations, and we will discuss about next turbine, that is your reaction turbine, Francis turbine, construction of Francis turbine and okay, thank you.